Hello students. So we continue in this particular week the discussion on the nature based solutions. And this week we have decided to discuss blue green infrastructure, environmental engineering, ecological engineering. These are the three major important components which we have discussed under nature based solution. And then we will be discussing the application potential for nature based solution and policy framework for nature based solution. So today we will be starting with the blue green infrastructure, and in this we will recap what is BGI and then BGI classification, matrix, corridor and patch scale, its design and performance. So the urban crisis is very strong and there is a need. For that only we are discussing this urban ecosystem, and this urban ecosystem has a major component on the nature based solutions where blue green infrastructure becomes one of the major type of nature based solution. What are the urban crises? Rapid urbanization and climate change both are actually increasing the vulnerability of the cities and citizens towards the flooding, heat stress, water crisis and biodiversity loss. Traditional grey infrastructures is static, aging and often overwhelmed by the extreme weather events. So, we are trying to move beyond single purpose engineering to multifunctional ecosystem services, and that is primary discussion point under the particular this course, that is urban ecosystem. So, what is blue green infrastructure? A strategically planned network of green and blue systems integrated with grey infrastructure to deliver multiple services like flood mitigation, thermal regulation, water quality improvement, biodiversity support, and human well being. There are three major components in the BGI which we need to remember. First one is the green, vegetation, permeable soils, trees, roofs, gardens for evapotranspiration and infiltration. There is blue, water systems, ponds, wetlands, canals, streams. They are actually going to be used for storage, conveyance, and cooling. And the third component, which is very important for this blue green infrastructure to be successful, that is integration. Combine blue green networks for multifunctional resilience. We also combine it with the grey infrastructure. So, the grey infrastructure, which is single function design, pipes, treatment plants, concrete, and centralized control and modular systems primarily, they use high capital and maintenance, limited co benefits, and aging fixed capacity. Whereas, why we are shifting to blue green? It is a nature based process, multifunctional design, distributed organic and modular systems, lower operational cost, multiple co-benefits, adaptive, improves over time. So for that only, there is a shift in the paradigm towards the ecological planning. Blue-green infrastructure, the spatial strategy, we'll be discussing first the patch corridor matrix model, PCM model. It's not physics, chemistry, math. It's a patch corridor matrix. Urban matrix, the dominant built environment. High density built up residential areas, commercial and mixed use urban fabric, informal settlements, industrial zones, road dominated urban fabric like concrete or asphalt. These are the today's urban matrix. But it used to be different as well. I will be discussing that. Urban corridor, rivers, tree lined avenues, flow of wind, water, species. Urban corridor act as ventilation channels to flush out heat and pollution. Urban patches, the remnant forests, parks, nodes of biodiversity, act as carbon sinks and cool islands. So the spatial strategy is softening urban matrix, increasing pervious surface from 10% to 25% via green roof, permeable pavements, streets, trees, that will reduce runoff by 35 to 45%. So, this softening of urban matrix is important. So from the concrete towards the pervious surfaces. Application creating greenways rather than isolated parks to maximize climate resilience. Goal is increase patch size, connect corridors and patches, and thus we will be able to soften the matrix. So we'll be discussing patch scale BGI, corridor scale BGI, and the matrix scale BGI. When we talk about scale, there are two different things. The scale may mean scale and size, and scale may means the impact. When we talk about PCM, the model, it talks about the impact which it is creating. So the matrix scale is the dominant background urban systems have, within which patches and corridors are embedded. Matrix quality determines overall ecosystem performances. So street trees as a citywide norm, permeable pavements, green blue roofs, if we have many, then it's a connected matrix can be. Rain gardens at city level, decentralized wastewater systems, courtyard greens in dense fabrics, but they will not be single isolated patches. There has to be repetition of that and the connection. Then it's a matrix scale. Corridor scale linear systems along flow paths connect patches and enable flows of water, species, air, people, and energy. It treats as well as slow down the flow. River floodplain systems, urban drains with vegetation, canal networks, biosoils, greenways and riparian buffers. They are good example of the corridor scale BGIs. Patch scale, non-dominant, spatially bounded ecosystem units that contrast with the urban matrix and provide concentrated ecosystem services. So, urban lakes, isolated ponds, tanks, constructed wetlands, urban parks, biodiversity park, institutional green campuses, detention, retention basins. So, if they are isolated, non dominant, then they are patch. But if they are very dominant, like in the city of Bangalore at one time, it used to have series of lakes, so that was a very dominant background. So then in that scale those lakes are matrix scale, whereas one singular lake is a patch scale which is having its own spatial boundary. First we will be discussing rain garden, which is a shallow planted depression that collects and absorbs rainwater from surfaces like roof, yards, driveways and streets. So from wherever it can collect, it collects that water. It utilizes native plants with deep roots to filter water, allowing it to seep into the ground. You can see in this figure the deep rooted plants, the bomb, you have to have a bomb to control this. And these are the inlets, the gutter and downspouts, they are bringing the water inside. And what they are doing, they are this through their deep roots, the plants are actually encouraging infiltration and helping to absorb the nutrients. Where we can apply the rain gardens, we can go for alongside the roads, sidewalks, and driveways. Building edges, you can go for a rain garden, courtyards, parking lot islands. In many parking lots, it's actually encouraged to have a rain garden because it can also filter that water. It can really improve the quality of water. It can trap that grease as well, grease and petrol. Performance peak runoff, it can reduce 60 to 90% if it is a small event. Total suspended solids, TSS, it can remove 45 to 72%. Phosphorus removal is also very significant, like the nitrogen one. So, very win-win scenario with rain gardens. It can be a matrix as well. Let us see how to really go for the technical drawing for this rain gardens, because actually you have to really create it. We discussed about the knowledge, that how to introduce the NBS. One of the major challenges having the knowledge. So you can just look at this particular section where you see this is the main rain garden, where the media, which is having the depth 375 to 600, the width is 450. Here you create the soil, it's a structured soil, so that the water can go down with some good amount of filtration. And the water will come from anywhere as it is coming through this side, and this is that bed which you can find here. And this is the very interesting, always any water body, if it has been properly designed, it will have a overflow opportunity. So this is that overflow opportunity. You can see that bomb here which I was showing. This is the top part of the bomb and this is the total bomb. You can see the bomb here and the slope, that 4 in 1 and 2 in 1, that is also the inside slope is 2 in 1. So these are the different technical data which you require when you design a rain garden for certain places. Drainage area up to 1000 square meter per garden. You can drain up to 1000 square meter per single garden. Surface area 5 to 10% of contributing impervious area. Ponding depth 150 mm, 24 to 48 hours retention. Filter media 375 to 600, which I discussed here as well. Sand, compost and loam. There will be a structured composition. Infiltration rate 25 mm per hour. It will be more than that, field tested. Distance from the foundation, if you have a building or something, from that minimum 250 mm, but 3000 mm is preferred. Slide slopes, as I said, 3 is to 1 to 4 is to 1. It can be also 2 is to 1 on the inner side. Corridor scale BGI will be discussing. That is, the first one is the bioswale. Linear filtration is shallow, sloped vegetated channel designed to collect, slow and filter stormwater from adjacent surfaces, roads, parking, sidewalks. Where we can find it? Roadside, medians, parking lots. You just see a beautiful bioswale in the median. What it does, it can collect water and infiltrate. Filtration and pollutant removal is another function we get out of bioswale. Cooling and aesthetic benefits, because we are also having trees on top of it. We are also having the ground covers here. Slows down water through this. And groundwater recharge. If it is directly connected, we will have the groundwater recharge. And we will also find one very interesting thing, that we can further engineer it. We can also have a underground drain that can be perforated. I will show that in the details as well. You just see that this is that under drain, perforated under drain, which can bring the water here and it can get percolated further. So not only we are doing it on the top here bioswale where we have created this, but also we can continue to do that deeper down if that particular area receives lot of rainfalls. Otherwise, it can be a very simple open drain, or you can go for much more refined engineered layers in it. So, longitudinal slope, bottom width, ponding depth, soil media depth, infiltration rate, drainage area per segment, drawdown time, all these are going to be design parameters, and we can find that for each one of them already we are having existing specifications, like bottom width needs to be 600 to 1400 mm, ponding depth 150 mm, drawdown time 12 to 48 hours. So every time you can see it's a retention only, it's not detention. So which is preventing the water logging as well as mosquito breeding is also prevented. Pollutant removal effectiveness of the bioswales are very, very significant. TSS 70%. NP, nitrogen, phosphorus, heavy metals, everywhere it shows wonderful performance. So, bioswale is one very easy thing where we can see that it's a linear one, but at the same time, it provides an opportunity not to have the flooding, but to have the groundwater recharge. Another variation of this bioswale we can find in the filter drains. In the filter drains, which is also known as French drains or perforated pipe drains, So we will have a pipe here. That's the difference between the bioswale and this. In the bioswale, it was open fully. This shallow trench is filled with gravel crushed stone, often containing a perforated pipe. I will show you that perforated pipe arrangement through a technical drawing. And this pipe is collecting and conveying stormwater runoff while allowing it to filter through the gravel, because it is having perforation, and while it is filtering through the gravel, then the filtered water is getting recharged. Suitable locations: roadside verges, parking lot edges or medians, footpaths and cycle tracks, perimeters of sites. So, everywhere we can go for French drains or the bioswales. Many of the campuses now actually looking at them very seriously because they don't want to lose even a single drop of water. And compulsory element goes from the BGI side is this drains. Filter drain, I was telling you about this technical part, that it's a normal one. You are having this slope, and below that you have the engineered soil through which it is getting percolated, and you just see there is the drain. This drain is actually under drain pipe which is having the perforations, and the gravels are helping that water to be sipped in. So again, the design parameters are, the ranges have been given: 300 to 1000 mm width, depth is 600 to 1200 mm, clean aggregate plus geotextile. Geotextile is always being used. Perforated pipe optional, 150 or more than that the diameter. Separation 1 meter minimum from the water table. So you don't touch the water table. You keep a separation of 1 meter. That is very important. Slope is 1 is to 50 to 1 is to 400, provided you get the space. TSS removal is very high in this case as well, and this TSS removal is very important because soil erosion is getting controlled. So, can you understand what different benefits this type of NBS through the BGI can be brought to the cities? Riparian buffers. So, most of the cities are actually having that fortune to have the rivers, streams of different sizes. But somehow we are so very unlucky that in India we are not being able to maintain those streams or the environment flows of the rivers. Riparian buffers are really going to be very important to protect the streams. Vegetated zones adjacent to water bodies, rivers, streams, lakes that transition between land and water. They stabilize banks, filter runoff before it enters the water body, so better quality of water is coming to the water body, and provide critical habitat for aquatic and terrestrial species. Suitable locations along the city rivers, lake perimeters, edges of urban drainage channel. So the riparian buffers are also to be designed properly. The width 30 to 100 meter from the waterway edge is ideal for full ecological function. The vegetation has to be deep rooted, native grasses and trees to prevent soil erosion and withstand periodic inundation. Pollutant removals designed to capture 80 to 95% of sediment and 85 to 90% of nitrogen from the surface runoff. And you can really look at this particular conceptual drawing where it talks about the how the organic surface flow of water, how the nutrients are being taken by the roots, and whereas it is restricting the entry of pollutants like phosphorus and nitrogen is being uptake by these trees. Also it is restricting the solid waste entry in the stream. So that has to be done. So it's not only the design and implementation, it also needs the monitoring. Preventing from the eutrophication will happen. So this is something riparian buffer which will not only help the city, it is also going to help the stream as well. The next example will be from the matrix scale. Permeable pavement, because throughout the city I can have the permeable pavement and it can become a dominant feature. So permeable pavements are specifically designed, all of us we know, which allows the rainwater to go down. So what happens here, you just see permeable joint materials are there, and below that uncompacted subgrade soil is there through which it can go down. And even if you are using asphalt or concrete, nowadays the options are there for pervious concrete, porous asphalt. So these are very nicely uh, integrated. And whatever water is coming, that if you are using the drain, then you can go for the perforated drains as well. So, suitable locations, parking lots, parking bays, footpaths, sidewalks, and pedestrian plazas, bicycle lanes and campus roads, courtyards, and open spaces within complexes. We discussed about greenwashing. In many places, I have seen it's this permeable pavements are being used as greenwashing, because below that permeable pavement this is a solid concrete one, then it doesn't have any meaning to be it is not actually a permeable pavement. All the layers needs to be designed appropriately. Design parameters: porous asphalt, pervious concrete, grass pavers. Then runoff reduction is 70 to 80% of annual rainfall. TSS credits are there. Base course is going to be of clean stone. Permeability 1000 per hour minimum. So it's a very highly permeable. Maintenance, vacuum or pressure wash every 2 to 3 years, so that this particular permeable joints are not choked. Thermal benefits: reduces UHI, lighter color, permeable, that are the benefits if you try to go for the thermal benefits. And one thing you can do, you can look at this particular technical drawing seriously, because in many cases you will be able to advise the technical detailing of these permeable pavements. Next one we'll be discussing is the urban forest, which comprises large-scale networks of trees in cities, including street trees, remnant woodlands, and forested patches, designed to function as the lungs of the cities. The suitable locations: public rights of the way, institutional campuses, buffer zones. Beyond the decorative landscaping, these urban forests provide dense canopy cover that mitigate UHI, intercepts rainfall, delivers key ecosystem services like carbon sequestration, air filtration, and habitat. Trees per kilometer: 50 to 200 trees. Ground coverage: you can target 10 to 40% coverage of the total streetscape width. Soil volume: minimum 15 to 25 cubic meter of uncompacted soil per large tree to ensure health and stability. And select the species with 40 to 80 plus years of lifespan to maximize carbon storage, because these days we are also having that discussion that if the trees are dying very fast, then it is not really helping in carbon storage, rather it becomes a source of carbon itself. Next thing we will be discussing is the urban parks, which are managed open spaces that function as infiltration sponges and biodiversity hubs within the built environment. And they are used by the people as an amenity. They provide mass cooling through evapotranspiration and offer temporary flood storage during extreme monsoon events. Suitable locations: neighborhood centers, floodplains, brownfield sites, they can be suitable location for the urban parks. The minimum size shall be half an hectare to achieve measurable microclimate cooling. More than 60% of the park area should be permeable: grass, shrubs, trees, etc. Native soil infiltration rate shall be 10 to 50 per hour. Amended soil used in the depression zones, so that quickly it can get infiltrated. Urban parks are having a cooling radius of typically 300 to 500 meter into the surrounding urban fabric. Next part we will be discussing this BGI design. designing connected BGI systems, hybrid infrastructure, and BGI for urban regeneration. So, first one is the designing connected BGI systems from sites to networks. Single BGI element will not provide city scale resilience. So, we need multiple patches connected by corridors, functions as the emergent matrix system. So, network components will be core patches, corridors, stepping stones, small infiltration zones, trees, green roofs, etc. Sink nodes, treatment wetlands, sedimentation basins for quality improvement. What are the design steps one can follow? First, one can identify the core patches via GIS suitability map. Then you can map potential corridors using least cost path analysis. Next, filter to priority corridors via the gravity model, which comes out of the interaction strength. Detailed design of the corridors will follow next. Width, vegetation, under drain, all the details which I was showing you previously. Phase implementation by feasibility, funding, and land ownership. In Ahmedabad, they have done these sites to networks, designing connected VGI and 120 corridors. Initially, they started with 11 square kilometer corridor areas and 26 square kilometer core patches. So, total 37 square kilometer of total network, serving 450 square kilometer of the study area. So, these are very good case studies which can really make us excited to understand better and better of the BGI system. It can be BGI also can be an hybrid infrastructure while integrating with gray system. So gray infrastructure like treatment plants, large pipes is not obsolete. You need it in urban ecosystem. So best practices is green plus gray and not either green or gray. So traditional grey, which we already know, is not being able to face the challenges of today's urban risks. So hybrid approach, the best practices will be going for distributed BGI, first flush treatment, infiltration, etc. Smaller right-sized pipes convey treated water only. Decentralized water treatment and central backup. Multifunctional networks, flood, heat, biodiversity, lower operational cost, adaptive management, and upgradation. Outcome will be 30 to 50% reduction in grey infrastructure size, cost savings, risk distribution, no single point failure. And if we are having that reduction in grey infrastructure size, that means we need not to actually go and change the size. The size itself will have the existing size of the grey infrastructure will be able to manage larger loading. Cascading treatment improves final water quality by 80 to 95%. So, you get the benefit of this nature based treatment without spending on the chemical treatments or any other treatments. Now, the third important one we will be discussing is the BGI for urban regeneration. Very important in today's urban ecosystem. Post industrial and brownfield sites. Post mining lands, coal, laterite, limestone, if that is the type of site. Excavation, restoration as ponds, phytoremediation with native trees, renewable energy sites, that can be the BGI strategies. Co-benefits will get biodiversity restoration, water security, energy transition. In the cities we have lot of abundant industrial sites, steelworks, textile mills, etc. There also we can integrate BGIs for remediation of soil, installing green corridors, detention basins, mixed use development we can carry out. It can be part of the heritage tourism, cultural regeneration, flood mitigation. The other two types we'll be discussing, they are the landfill closure and capping and urban wasteland, informal settlements, unauthorized occupation, etc. BGI integration for the landfill will be capping the impermeable layer, construct extensive green roof ecosystem. So landfill gas recovery, stable land use, public park amenity, they will be the co-benefits. For the wastelands, land consolidation, participatory design, pocket parks, microhabitat creation, etc. can be the BGI strategy. Benefits will be slum upgradation, livelihood creation, climate resilience. And in India, we have extensive post mining and industrial degraded lands. Similarly, landfill and wastelands also needs serious attention from the planners. So BGI can transform them into resilient green urban cores instead of being a problem for the city. The next and concluding section of this lecture will be the BGI performance. We will be discussing it for the heat, pollutant removal and the water. Urban heat island mitigation, we talked a lot about the BGI's efficiency. Green roof, extensive urban parks, it has to be as discussed earlier, more than half a acre. Large water bodies, lakes, ponds, street trees, canopy shall be more than 30%. BGI network integrated. So in these cases, we can see many different cooling mechanism, evapotranspiration, vegetation shading, mass cooling, advection, and combined albedo effects as well. And temperature reduction ranges very widely. On the roof, 15 to 25 degrees Celsius. Within park, 2 to 5 degrees Celsius. 1 to 2 degrees Celsius at the neighborhood. 2 to 4 degree at 500 meter if I have a water body. And 1 degree Celsius up to the 1.2 meter distance from the lake edge. 3.8 degrees Celsius, 3 to 8 degrees Celsius under canopy, 0.5 to 2 degrees Celsius in streets, 4 to 8 degrees Celsius city wide. So there are n number of different type of ranges for different type of blue-green elements. We have seen that 10% reduction in the building density can reduce the UHI, 20% cooling by the pavement and 20% once gets increased the cooling if we are using the green and water. So that's the way the optimal UHI reduction model has been suggested by the scientist. But that is for a typical temperate climate. So next one will be discussing the pollutant removals. So total suspended solids, total phosphorus, total nitrogen, heavy metals, oil and grease, bacteria, all these can be removed through mechanisms like settling, soil filtration, absorption to soil, plant uptake, denitrification, sorption, complexation, settling, infiltration, soil filtering, predation, decay, etc. And the removal is very optimistic, up to 90%, sometimes it's almost 100% we can see. So design factor will be for different pollutants different. So like in the heavy metal, soil pH, organic matter will matter. Total suspended solids, soil depth, detention time will matter. In the oil and grease, mulch layer, filter media depth, they will matter. So these are the different design factors. The performance of these BGIS element are highly variable. Soil infiltration achieves reliable removal. Underdrain systems achieve lower pollutant removal unless inline treatment is added. The last one we will be discussing for the performance is definitely the water, the hydrological metrics. The key question, how much runoff is reduced, at what peak flow, for what rainfall event. So these are the questions which you try to answer through your design. Your metric will be volume reduction, peak flow reduction, time to peak, infiltration rate, water quality improvement. So the definitions and units you will be using, that is percentage of annual rainfall, percentage decrease, hours delayed, mm per hour, percentage reduction in pollutants, etc. So, temperate performance and tropical monsoon performance, these two will differ havoc. So, you have to also look at the Indian context and accordingly you have to select. Design for monsoon reality, do not copy these temperate zone target reductions. That doesn't happen here. So, key takeaways and way forward for these BGI elements will be shifting the paradigm from the either green or either gray to holistic green and gray. The goal is a hybrid system where distributed BGI handles first flush treatment and infiltration, allowing gray infrastructure to be right sized for conveyance. The power up scale, a single rain garden like patch is insufficient. Resilience requires connecting these patches via linear corridors, biosoils, and embedding them into a permeable matrix to form a functional citywide network. Biodiversity as engineering. Vegetation is not just aesthetic, high diversity planting improves hydraulic performance, better retention, enhances cooling like higher evapotranspiration, and ensures long term system stability. And that is important to understand and design. So, today we have discussed in this lecture the BGI, as classification, patch, corridor, and matrix, PCM. We have discussed BGI design as connected system, as hybrid system, and we discussed the performance for the heat, for the pollutants, and the water. These are the references, series of references, and thank you.